Okay, I think we will get started. Okay. Um, Good morning. It's still morning, right? So good morning. So you guys, most of you probably know who I am, so that I'm extremely happy today to introduce today's speaker. Dr. Uh, we always call it Longfei Shangguan, right? So that even for some of the Chinese people, probably we normally the last name is like one character, but he has two characters. So I have been knowing Longfei for a long time. So in private situation, he always claimed that he's my academic grandson. So this pushed me became like really old. So I didn't want to use that as an official introduction here. But Longfei has been doing, getting his bachelor degree from Xidian University, so where I also myself graduated from back to about almost 30 years ago. Yeah, so, and then he did his PhD at Hong Kong University of Science and Technology. And his advisor and I, we are actually a very good friend. So after that, he's spending some time at Princeton, right?
Yeah, Princeton.
Yeah, as a postdoc, and then joined the Microsoft Research Redmond in Seattle, all the way go to a senior research, and most recently joined the University of Pittsburgh as assistant professor. So that's just a little journey about him. What I want to mention is, as you know that since I joined the department, we really pushing for this top publication in the top conferences, papers, and etc. So if you're looking for Longfei's webpage, so if you take a look of that, you will see that this is one of the person that I don't count, but I guess in his such a short career so far, he probably already have more than 20 CS ranking papers. So if we put him in our department, he will be, as of today, most likely either top one or top two. That's just to give you an idea about that how productive he is. So I think given this talk, in his field of research, he basically is working on low power, wireless, embedded system, etc. But I want to open it more that take this opportunity, ask him, how can you publish, in this top, choosing the topic, and how do you write in the paper, publish the paper, eventually can be published in this top places, such as NSTI, Mobicis, Mobicom, many of these places. So without further ado, I will give the podium to him. Okay, welcome.
Thank you, Tom. Thanks. I mean, yes, my academic grandfather. Thanks for the nice words. So, hello everyone, Longfei. So, glad to be here to deliver a talk on my research. So, today I'm gonna talk about some of my past works on specific one line of my research on building low power wireless systems. So I have been working on this area for more than 10 years. So yeah, we have a lot of paper in this area, but today I want to use few examples to sort of showing how we dive into this area, how we rethinking the problems, identify the problem, how we solve these problems. So more importantly, I want to share some lessons we learned from building these systems. So I'm a system builder. I love building systems. I build this system to validate research hypotheses, to understand the theory, and more importantly, we build this system to train the students into independent thinkers and brave explorers. So I moved to Pitt last year. So currently I'm directing the lab called the PERCH, Pittsburgh Experimental Research Lab. So it's a highly interdisciplinary lab, and we have one postdoc and 3 PhD students for now. We do build, we do hack, we do break the software, the hardware, and of course the boundary between them. So in the past few years, since 2011, I start in my PhD career, start building stuffs. Initially, I'm working on building these mobile systems. When I'm a PhD student in Hong Kong, for example, when more and more sensors are showing up on smartphones, we start building like mobile sensing system. How can we leverage these sensors on smartphones to like track our human beings, track like, your behaviors, so on and so forth. And for example, when more and more RFID tags are showing up, like we build systems to sort of like, go RF like beyond RFID. For example, by attaching these low-cost RFID tags on the stylus on a pen, we can build this RF tracking system, like track your handwritings. So with antenna array, you can even track your like human writings in the air. We know for our human beings, this could be another way to interact with the machines, the objects, and many others in our ambient environment. So after I got my PhD, I moved to Princeton, starting my postdoc. So I slightly delved deeper into, for example, middleware, the OS, the network stack. We start building like, efficient, versatile network stack to optimize, to make it more like, robust to different wireless variations, conditions, multipath, so on and so forth. So like, as Alan said, like people who are really serious about the software should build their own hardware. So following Alan's calls, we start building hardware. We start building this hardware from scratch. To this end, we built a lot of like, RF hardwares, like, ultra low power, no battery are needed. We also built those like low cost acoustic radios, which can support us to do ambient sensing. All right, so today I would like to summarize some of my like research experience by taking a retrospect of the backscatter system. So as I briefly mentioned in the beginning of this talk, I've been working on this area for more than 10 years. Like, from early stage, like we start using RFID to build the tracking system. So indeed, we built the world's first relative RFID localization system, which has been deployed in the Peking Capital International Airport for baggage tracking. So after playing with this like commercial off-the-shelf RFID tags for a few years, we actually found a lot of drawbacks with existing commercial off-the-shelf RFID devices. So we start building our own hardware, start building our own RFID tag. So to this end, we built the world's first long-range RFID system, which can efficiently expand the communication range of the conventional RFID tag from tens of meters to kilometer scale. And we also have a test bed deployed in the Mount Chilian for golden monkey monitoring. So once we have this hardware, we start thinking, can we use this hardware to enable many other new novel applications? And to this end, we find these hardwares do, show some promising effect on some like, exciting areas. For example, we leverage our backscatter radios to build this embodied wireless charging system. So today I'm gonna, talk about these three systems, like, how we identify the problem and how we like, propose the solution to solve it. And more importantly, the lessons we learned from building them. And at the end of this talk, I'll briefly talk about how we leverage this license to develop new research directions. So yeah, this is pretty much what I want to talk today. So to start with, I think most of you may have a simple, question. Why RFID? Why do you want to build RFID systems? So to a system builder like me, RFID is interesting because, first of all, RFID is the, cheapest computing unit on the market. We use RFID every day. Like, there are billions of RFID tags deployed in malls, in supermarkets, almost everywhere around us. So if you can sort of take it as the world's largest distributed system, then like you can sort of like building many exciting stuff, right? But this is not enough. This is not enough for a PhD thesis, right? So this is exciting, but what's the technical challenge behind, right? If there's no technical challenge and, or the technical challenge already been solved, then there's no way for you to put up a PhD thesis, right? So RFID is very cheap. like 5 cents. But there's a lot of fundamental limitations with RFID. For example, like they have very limited storage. They have no battery, so they got power from the ambient signal from, for example, a carrier signal sent from a RFID reader. So, like you can see, the conventional RFID tags only support identification purpose, like you store a tag ID on the tag and put a tag on a clothes or piece of clothes or whatever, like a book. So it only serves as a identification purpose. So if you want to do something cool using this RFID system, you need to go beyond, go RF beyond identification. So this is a primary challenge we have. So I think for most of the students, I think the first project, is about application, right? So how can we come up with application leveraging this, unique technology? So likewise, my very first project is trying to answer a very simple question: where's Harry Potter? So where's the book? We know in the library there are millions of books, right? So if you misplace the book in another place, it's almost impossible for the others to find it, right? So that's why every year, for the libraries, the librarians need to visually check each book on each layer of each bookshelf to find those misplaced books or missing books. So apparently this is not an ideal solution, right? Because people may get fatigued, right? Make mistakes. So that's why even after this manual sorting, there are still a lot of missing books or misplaced books. So as a system builder, like what we care about is like whether we can build a autonomous system to replace this labor-intensive, error-prone, like human sorting process. And we find that actually we can give affirmative answer by using this RFID technology. So here are two opportunities. So first of all, we noticed that most of the libraries have already adopted this RFID technology to manage their books. For example, they usually attach a book, on each attach RFID tag on each book. So the tag will store ID corresponding to the title of this book, which essentially means that as long as you can find the tag ID, you know where the book is, right? So when you're putting the books on the bookshelf, you can see the location of these tags actually reflects the location of the books. So apparently, if you can localize this RFID tag, you can definitely find those missing books or misplaced books, right? This is a very intuitive, relationship. So notice that we start to literature review. We start thinking which kind of technology could we leverage to address this problem, right? I think this is a normal way to address a research problem. So we take a long time to implement a lot of solutions like our flow validation systems. We found that actually none of these solutions would work for our scenario, for our specific scenario. Why? First of all, at that time, dating back to 2011, most of these RF localization systems, actually they do have a very large localization error. For example, at that time, the state of the art can only achieve meter level localization accuracy. But what we need is a centimeter level, right? Because the book, just a few centimeters. So we have to figure out how to localize the books in a very fine-grained granularity. Another, primary hurdle here is that at that time, most of these localization systems, they do rely on this bulky antenna array, because you can, with antenna array, you can tracking the angle of arrival of these RF reflection signals to localize where you are. So to localize it, you need at least 3 antenna array. But given the limited coverage area of each, antenna array. Think about to cover the whole array, how many these arrays you need to deploy. It's actually millions of dollars for the infrastructure cost, which is definitely not a, good solution. So notice that we start rethinking this problem. Do we really need to know the location of these tags? We found that no, we don't need that. What we need is actually a logical location, right? So what I really need is just a tag order. If you just tell me like which layer this book was, and from the left to right, the number of this book, this is enough for me, right? Because this is the most intuitive metadata to our human beings to find the books, right? So in other words, we do not need an absolute XYZ location. We only need a relative order. So notice that we come up with a very, very simple solution, which is very cheap and can achieve a very high accuracy. So here, let me tell you how this simple idea works. So suppose now you have a RFID tag, okay? So we have an RFID reader antenna. So when we move this reader antenna from the left to the right, we know the distance between the tag and the reader antenna gonna change accordingly, right? So this distance D here will decrease first as reader antenna approach to the tag, and then move away as and then increase as the reader antenna moves away. So basically, this distance D will achieve its minimum value when this reader antenna is in perpendicular to this tag, right? This is simple geometry. So when the reader antenna sweep these RFID tags, it's gonna query this RFID tag multiple times at different time slots. So from the text reply, we can obtain a parameter called the phase. So phase is actually describing how the distance between the tag and the reader antenna changes over time. So here, as you can see, as the reader antenna sweeps the tag, we're gonna get a phase changes, continuously, for example, from 2 pi to 0. But when the reader antenna surpasses this perpendicular point, we know the distance is gonna increase again, right? So the phase is gonna reversely changing, right? So when we plot these phase readings on the time domain, you can see actually this phase shows a symmetric pattern here, right? So this symmetric point is actually corresponding to the perpendicular point where the tag is in perpendicular to the reader antenna. So this is a simple geometry we have. So now suppose you have 2 tags, and when the reader antenna sweep these 2 tags accordingly, we're gonna have 2 phase profile for each tag, right? So by simply identify the perpendicular point on each phase profile, you can get the time point when the reader antenna surpasses tag and sorting these tags accordingly, right? So you can see here, what we need is a single antenna, and you can put it on a Roomba, let it move, steadily to save the tags. You're gonna get this profile and obtain this perpendicular point, time point to figure out their orders. Well, we have a very simple idea to sorting the tags along one dimension, but we know the bookshelf already have multiple dimensions, right? They have different layers. So how could we obtain the order along another dimension? Well, you can definitely moving the reader antenna along the y-axis again to use the same principle. But this sort of brings some troubles to the real deployment, right? So we were just wondering, can we just sweep the tag along one dimension and then obtain the tag order along 2 dimensions? We find this is also feasible. Also, the basic principle behind is quite intuitive. So as you can see here, we have 2 tags. tag 1, tag 2 along the y dimension. We know as the read antenna moves, the distance d between tag 1 and the read antenna is always larger than the distance between the tag 2 and read antenna. So as the read antenna moves, the distance changing rate of the first tag 1, is actually always smaller than the distance changing rate of tag 2, right? This is just a simple mathematics. I think the high school mathematics can. So remember, phase is actually characterizing how your distance change over time. So we are expecting to see similar trend on their phase profile. So the larger the distance between the tag and the read antenna, the slower the phase changing rate you're gonna have. So by observing how their phase change over time, we can also determine the tag order along the y dimension. So this is the idea behind. Of course, we have many practical challenges, like how to deal with the multitask. But here, I just to deliver a basic idea how we rethinking this problem to solve it. You have a very, very simple idea. So apart from the book sorting problem, we found actually there's another very exciting application can directly benefit from this technology. That is a book sorting in the that is a baggage sorting in the airport. When you're checking your baggage will be delivered to a very big sorting pool. And then the laborers or workers there will staring at the labels on your checked-in baggage and get it and sort it to the corresponding cart and deliver it to the corresponding flight. So that's why baggage missing happens, because you're gonna make some mistakes, deliver your baggage to the wrong bin, right? So we found that our system can sort of benefit this labor sorting process. So this is actually the photo. So showing on the left side is the system we built called the tag assist. So we do have the multiple read antenna on this tag assist system. We call it track tunnel. So for each checked-in baggage, we have to put RFID tag on their label. So when this baggage goes through this track tunnel, we're gonna track their orders, like you can see here. So different color represents a different flight number, and also we will show how many baggage has been already being delivered to the corresponding flight, how many baggage are still left on the moving conveyor. So with this information, actually you can the workers can directly know how many baggage has been sorted, and to avoid these baggage missing cases. So here's a short demo show our real deployment in Peking Capital International Airport, which once was the world's second largest airport in the world. So we have this track tunnel, we have this monitor to show the real-time status of this baggage on the moving conveyor. So this system has been deployed in Peking Capital International Airport for many years. I think for now, they may still work there. I hope so. So, all right, I briefly talked about the basic idea behind this system. But when we develop this system, we also find a lot of problems with this commercial off-the-shelf RFID systems. For example, we found that these RFID tags heavily rely on this dedicated RFID reader. The tags are very cheap. The tags only cost 5 cents. But the RFID reader usually costs 2,000 baht, 3,000 baht. So making the whole system still very expensive. Another problem with the commercial off-the-shelf RFID devices is their relatively short communication range. So you can see the tag relies on the the carrier signal sent from the RFID tag, and then modulate this signal, send it back to the RFID reader for decoding. So due to this round trip signal accumulation and also the insertion loss at the RFID tag, the communication range between the tag and the read antenna is usually at tens of meters. So as a result, we can see most of these RFID systems are still like primarily being used in indoor applications. We can never deploy it outdoors because there's no power source. And like, their communication range very limited. So noting that, we start building our own hardware. We start building our own hardware from scratch. So we start building these long range backscatter radios. So when thinking about building a new RFID tag backscatter radio, then the first problem we want to answer is what can be the carrier signal, right? Because we want to kick away the RFID reader. If the RFID reader is missing, then where's the carrier signal, right? How could we modulate data? How could we convey the information from the tag? Well, although we don't have the RFID reader, but we noticed that actually we do have so many ambient wireless signal around us, right? Indoors, we have the Zigbee, we have the Wi-Fi, we have the Bluetooth traffic all the time. Outdoors, we have the LoRa, we have the LTE, 5G is on the way, right? So what if we can use this ambient signal as a carrier signal? So here, the following up question is which ambient signal should we use? Because we have so many options, right? To answer this question, let's take a step back, rethinking the goal of our project. So our goal is to sort of building a long range backscatter system, right? Communication system. Then the communication range is actually the primary factor to determine which technology we want to use. Then a newly emerging technology called the LoRa, jump out. So LoRa, they actually use a so-called chirp modulation to modulate data. So chirp is a frequency modulated signal whose frequency gonna change linearly over time. So when you want to modulate the data, you're gonna shift the initial frequency of the chirp to indicate which information encoded on this chirp signal. For example, if you want to modulate a bit 00, you can use a basic chirp whose initial frequency of set is 0. And if you want to modulate a symbol 01, you can slightly shift the initial frequency to delta F1. Likewise, you want to modulate symbol 10, you can change the initial frequency of set as well. So once the receiver receives the chirp signal, they're gonna multiply this chirp with the down chirp. Then after FFT, you can decode it on the frequency domain. So this signal processing gain allows this LoRa signal to transmit over kilometer scale, which is significantly longer than conventional Wi-Fi, Zigbee, and 5G. So this is an ideal carrier signal for our long-range backscatter system, right? But when you want to translate this basic idea into a practical system, there are still fundamental challenges. Remember, in the conventional RFID system, the carrier signal is a single tone. So the RFID tag can simply off key to modulate data. But the ambient LoRa signal, they have already encoded signals here. For the plural tag, plural is actually the name of our proposed backscatter radio. For the plural tag, if it wants to modulate some data on top of this ambient signal, it needs to know how this incoming signal looks like, right? But if you know how this incoming signal looks like, how could you modulate the data? This is a chicken egg problem. So to solve this problem, we still use a very simple idea, code word translation. So how this works? So suppose the LoRa channel, the LoRa node, conventional LoRa node, send an aperture. So if our plural tag wants to modulate bit 1, what we're gonna do is we will shift the frequency of this incoming LoRa chirp slightly to make it as a new chirp, which is slightly different from the conventional chirp. So the LoRa receiver usually has a quite high sampling rate, so it can, receive both of these chirp signals. It can simply XOR these two, chirps to decode this, encode information bit 1. And if you want to, modulate bit 0, you can simply reflect it back without modulating it. In this case, the ambient chirp, which represented by the blue line, should be exactly the same with the backscatter signal, which represented by the right line. In this case, the LoRa receiver can definitely decode this bit 0. So idea is very simple, right? But still, to implement this idea, there are still challenges. So the first challenge, still, you don't know how this incoming chirp looks like. How can you translate this incoming LoRa chirp into another standard LoRa chirp? Because the processing gain comes from this chirp symbol. If your modulated chirp is not a standard LoRa chirp, you're gonna lose some information and you're gonna lose some signal processing gain, which means that your communication range is gonna suffer. The second problem is when you modulate this ambient LoRa signal, you should make sure these two signals does not transmit over the same frequency band. Otherwise, you're gonna interfere with each other as receiver, right? So the receiver cannot decode both of them. So to solve these two challenges, we propose another idea called the chirp splicing or blind chirp modulation algorithm. Still, it is based on high school mathematics. So suppose now we are sending an ambient LoRa chirp represented by a blue line. So on our backscatter radio, we're gonna generate a very low frequency baseband signal. So represented by signal S2. So based on high school mathematics, we know the multiplication of two signals here. One is actually the ambient LoRa chirp. Another is a baseband signal you generated S2. So when you multiply S1 and S2 together, you gonna generate another new chirp signal at frequency A plus B and A minus B. So if we set up the B, so B is actually the frequency of your baseband signal and A is the frequency of your chirp. We set the frequency B to half LoRa bandwidth. Essentially, you are shifting this incoming LoRa chirp by half bandwidth and minus half bandwidth, as you can see on the right-hand side of this figure. So these two new LoRa chirps, part of them gonna be moved to the guard band, while the in-band part, you can see they are naturally spliced into another standard LoRa chirp. So indeed, we have proved that no matter how this incoming LoRa chirp looks like, by using this blind chirp splicing algorithm, we can always obtain another standard LoRa chirp. So here I use a toy example to show how this tag works. So this is actually a high-level sketch of our backscatter tag. So we have two RF chains. So if we want to modulate a bit 1, what we're gonna do is in the first RF chain, we generate a baseband signal at frequency F shift plus the half bandwidth. While for the second chain, we're gonna generate another signal at frequency F shift minus half bandwidth. So when this incoming chirp impinge on the first antenna, the first RF chain, the signal generated by the first RF chain, gonna shift it to F shift plus half bandwidth, right? Likewise, when it's impinged on the second antenna, you're gonna get another chirp on this new channel. So in this way, we do shift the modulated signal to another channel, which means that these two signals will not interfere with each other, right, at the receiver. In the meantime, we have successfully translate this ambient LoRa chirp into another standard LoRa chirp. So as I mentioned, we had deployed the prototype. So here's the demo about our deployment in Mount Chilling. So we had deployed a few backscatter radios here to sort of monitoring the habitat of the golden monkey, which is actually the cherry of China. So we do monitor the temperature, the humidity, and then leverage this backscatter technology to transmit all these ambient environment factors back to the gateway for data analysis. All right, now we have a very good backscatter hardware. We can support the long range backscatter communication. What can we do with this hardware? And it turns out that we can even put this RFID tag inside our human body to support this in-body wireless charging. So we know these medical implants becoming more and more popular and important to our human beings, right? We use this, for example, pacemaker to sustain our lives, right? While the technical advancement, is sort of progressing so fast, but the battery is still a substantial hurdle behind these medical implants. So we know although some battery can support the pacemaker for 10 years, but how about 10 years later? You still need to take a surgery, take it out, replace the battery, right? So this is not an ideal solution, particularly for those elders who suffer from the chronic diseases, right? Taking surgery may put a lot of dangers to them. So why not using wireless charging? I think most of you have been using wireless charging to charge your phones, right? So why don't we use wireless charger to charge our medical implants? So there are two fundamental problems here. The first is the charging efficiency is so low. So here, let me put an example to explain. So suppose we have the RF charger. We send a wireless signal, and this signal gonna attenuate when it propagates through the air and then inside your human being. Well, more importantly, as your wireless signal goes through your human tissues, like your muscles, your bones, it's gonna suffer a lot. You can see you're gonna attenuate about 50 to 100 decibel, which means that when it arrives at your pacemaker, the signal will be very, very, very weak. You can almost do nothing with this small amount of power. Well, single antenna is not enough. Why don't we put multiple antennas to do the beamforming, right? With multiple antennas to charge you, signal gonna be very, very strong, right? But this is not feasible because this is not safe. We know this signal gonna first arrive at your skin, right? So if you have a very, very strong signal, it's gonna burn your skins. So that's why this multiple antenna still cannot be used to charge your medical implant. Well, actually we found that this linear array, although this linear array cannot be used to charge your medical implant, but if you slightly change the layout of this antenna, for example, you put it in a distributed manner, you can sort of generate an energy ball. So which means that the energy only concentrate on small points in our physical world. So this distributed antenna array can sort of support you to do that. But still the fundamental problem here is if you want to do the beamforming, you need to do the channel measurement to get the channel state information SSI. So the SSI is usually, in the wireless communication system is obtained by channel sounding process. So, the sender send a signal, and then based on the preamble, the receiver can measure how the channel looks like. But in our scenario, obtaining the CSI is so challenging or even impossible because when you transmit a signal from the medical implant to the wireless charger, this signal gonna be very weak when it arrives at the wireless charger because the in-body part gonna, attenuate your signal a lot. In this case, you cannot obtain a very accurate phase information to do the beamforming. So to address this problem, we're actually seeking for some non-CSI, blind beamforming algorithm, and there are. So for example, here show how a typical non-CSI beamforming works. So suppose you have multiple antennas, you want to beamform towards this receiver. What you're gonna do is these three antennas gonna first, set a random phase rating, random phase, and sending out the signal. So when this signal arrive at the receiver, this signal gonna superimpose together, right? So the receiver gonna record the signal strength. Then in the second round, these three antennas gonna send another signal, but in this case, they're gonna slightly change their phase in the vicinity of their phase sighting in the previous round. So in the similar way, the receiver gonna receive the superimposed signal and measure signal strength. If the receiver finds the signal strength is going up, then the receiver gonna send back a 1-bit feedback to these three antennas, tell this antenna signal is going up. So you can continue on this direction. So once these three antenna got the feedback from the receiver, these three antenna gonna reset the phase rating in the vicinity of the phase sighting in the second round and resending the signal again. But sometimes this may not necessarily lead to an even higher power, because the phase, the slightly change of the phase may, when you add these two signals together, they may cancel each other. So in this case, the receiver gonna send another ACK to this antenna, tell them oh, you are in the reverse trend. You should go back to the second round to reset your phase. So based on these feedbacks, step by step, finally, this algorithm will converge to the optimal phase settings ultimately. So there are strong mathematical improvements to show this blind beamforming gonna converge to the optimal phase settings. So this is good, right? So apparently we can leverage this kind of technology to do the beamforming, to do the wireless charging. But there's still a fundamental challenge here. As you can see, the whole process takes very, very long time, right? You have the feedback sending, right? So it may turns out that each time the receiver here is actually the pacemaker. You can imagine the pacemaker each time it needs to send a signal to the transmitter, tell them signal is going up or going down. So it may turns out that after multiple rounds, maybe hundreds of these rounds, the power will be consumed up as a pacemaker. So this is definitely not a good solution. And notice that we find, oh, our backscatter radio can help. So what we do is we can replace these active radios inside your pacemaker with our backscatter radio. So when you send a signal to the medical implant, our backscatter radio is sort of like a mirror to reflect this incoming signal directly back to the receiver outside your human body. We know the signal strength of this backscatter signal is actually proportional to the signal strength received at this in-body pacemaker. So by observing how this backscatter signal strength changes over time, you can actually tune your phase settings at the transmitter to do the beamforming. So we do build this prototype. Of course, we cannot put the backscatter tag in the real human being, right? So what we do is we try to emulate this scenario. We built 50 pounds this pork belly, and we put our tags inside this Pork Belly, and then we leverage the orbit system in Rutgers University to to build this distributed beamformer. So here I would like to show you a simple power measurement result. So here we show the signal strength distribution around your pacemaker. So the pacemaker is actually located in the center of this cube. So as you can see, the power, surrounding this cube is quite low, right? But the power at exactly the pacemaker's location is quite high. You can see the color here turns to be yellow, which means that the power is actually concentrated in this specific location. All right, so this is about system we built in the past. So here's some lessons we learned. First of all, I want to share is anchor your sense of self in the flexibility rather than consistency. So why? As I briefly mentioned in the first project, when we start thinking this problem, we start exploring the state of the art, trying to re-implement those localization systems, but never works and they cost a lot, right? But when we were rethinking this problem, we found that what we need is just a relative location, logical location. So we do not rely on any of these bulky antenna array. So this is the power of rethinking. So what I want to deliver a message here is try to rethinking your problem, when you don't know how to deal with that. Sometimes maybe you just think too much about the problem. It might turn out to be a very easy problem, can be solved by a very simple problem. That's a simple solution. And the system researchers do appreciate this kind of thinking. To me, I think the good paper is not about selling your technology. It's more about selling how you think about this problem. This is the most important stuff people want to read from your paper. The second license, this is actually some license I also learned from Professor Lin Zhong, who is currently a professor at Yale. So these innovations always go spiritually. Initially, you can see when I start building my system, I start building a software system, localization system. And when I after finishing this system, I found, there's still a problem with commercial off-the-shelf RFID devices. So we start building our own hardware. So once we have the good hardware, we start thinking, how could we leverage this hardware to build a better software, right? So I believe this software, innovation always goes spiritually. So the third license I want to share is about it is much more joyful to share the joy with, than enjoy alone. So why? Because I've been working on backscatter for more than 10 years. I found there is a strong barrier of entry to this backscatter community. Because if you want to build your own backscatter radio, you need to know a breadth of knowledge, circuit design, wireless communication, the impedance matching, power management, so on and so forth, right? So that's why this is still a relatively small research area. So how do we get more people into this area, push the boundary of this area? We need to do something, right? We need to provide them something. So notice that last year, actually, we come up with this platform called the RF Transformer. So this is a open sourced, a unified backscatter hardware abstraction. So basically with this hardware, we provide some programmability. You can sort of generate any types of backscatter signals as you want. And also luckily we got 200K gift fund from ARDC fabricating hundreds of these RF transformer. Oh.
No, I mean, so you said.
Yeah, for free. Yeah. So we do we will send them around the world for free. Just send us an email. We will mail you 2 of these backscatter radios for free. I mean, yeah, free food. So yeah, I think I may have like 5 minutes to briefly talk about some research directions I'm currently working on, and also like based on the lessons we learned from the past. So the first, direction I want to briefly mention is a computational wireless. So an edge control point of view. So wireless spectrum is very scarce, but the computing resources are becoming increasingly powerful, right? So conventionally, when you're thinking about like 1G, 2G, 3G, 4G, you see like their baseband signal processing and their RF module are, strictly coupled together. So whenever you want to upgrade like 4G to 5G, you need to replace the whole base station, right? This is sort of wasting a lot of money. Now edge computing is here, and we have so many powerful PCs and GPUs and computing resources. How about offload all these baseband signal processing to the edge, right? If you can offload them to the edge, then you can think in the base station is just a simple antenna plus some RF module. So whenever you want to like upgrade it to like 6G or 7G, what you need to do is just like replace antenna, because all the core signal processing is on the edge. This can be upgraded as a like software patch, right? So this can greatly facilitate this, upgrading the, telecommunication upgrading. So I can see this kind of edge control can provide us many benefits. For example, one of my students is currently exploring whether we can use the RT core on modern GPU, the ray tracing core, to expand its spirit coding, which is a very computationally intensive algorithm on wireless communication. Another benefit is that since you have the global view of this wireless radios, you can sort of control them to handle some extreme cases like mobility, right? You can leverage the central controller to deliver this high throughput wireless link to these highly mobile devices. And also you can leverage them to program the radios. So conventionally, we know if we want to, conventional thinking treats the wireless channel as a constraint. So what they do is they optimize their transmission signal to best fit the environment. But if we have this edge control plus some metamaterial or some programmable radios, we can sort of change our radio environment to make the radio environment best fit for your devices, your wireless devices or wireless access point. So another direction I want to briefly talk about is earable for social good. This is also another research direction I'm currently working on. So we know earbuds are embedded devices that can be placed in around our ears to sense our physiological activities. So we do have wearables, right? We have Apple Watch, we have the Fitbit wristband. So they are suitable to to sense our lower body activities. But for the earbuds, they are more close to your head, to your heart, so they can get a better signal from these important organs. So the conventional way on designing earbuds is trying to put more and more sensors on these earbud devices to sense this type of physiological signals. But you can see as you put more sensors, the device becomes bulky, become costly. So apparently, this is not a good design, approach or solution for those underdeveloped world, right? People who just earn $5 a day. So notice that we were thinking, can we design or can we, propose this very low-cost earbuds for the underdeveloped world? So actually, we do start this thread 2 years ago. And we find that indeed we can build a very low-cost plugin, which can, turn your everyday earphones into a smart earphones to sense your heartbeat, to sense your breath, to monitor your daily activities. So 2 years ago, we started this thread and our work of the festival run up and MobiCon 2021. And along this thread, we are currently working on 2 threads. The first is building this hardware platform. So we want to build a new earable computing hardware platform to benefit the entire community. Another direction is on building the earable for health. For example, we leverage these earphones to turn the earphones into a stethoscope for cardiac auscultation. This is actually gonna show up on MobiCon. Apart from that, we are also collaborating with industry. We are collaborating with Google to turn their earbud into a health tracker. So this is actually the APJ data is actually the heartbeat signal we got from the Google's earphone. So we do not put any PPG sensor, dedicated sensors on their earbud. We purely use their speaker and microphone to measure your heartbeat. So this is also gonna show up on MobiCon 23. So lastly, I would like to, I think I still have a few minutes, right? Or do you want me to stop here or?
Maybe stop here.
Okay,
We let them take some questions because I know some
Sorry
of
about
them,
that. Yeah.
some of them want to get a free your IF transformer.
Sure.
Come here. Yeah.
Sure.
Any
Okay.
questions from the audience?
Yeah, I'll stop here. Sorry about that. Yeah.
It's okay. He's not far away. Our neighbor, right? Go ahead.
I was just wondering, from way towards the beginning, with regards to using the RFID for positioning an order, is noise a concern at all for that? Is it relatively because it seems like if you've got 2 very thin books close together, then differentiating those phases, if there's any I was wondering if there's any sort of noise that might cause errors in the order.
For sure. Yeah, they do. For example, they do have if you can take the RFID tag and the antenna. If the 2 antennas is too close to each other, they're gonna couple together. They're gonna interfere with each other. So the receive signal can be sort of a mess. So we do have some detailed signal processing algorithm to deal with that. But yeah, at this talk, I did not mention too much about the details here. So yeah, sure. Another questions?
No questions? So I do have a question on this.
Sure.
Because you get your bachelor actually is in the
Software engineering.
software
Yeah.
engineer at your bachelor, right? So it looks like this is pretty broad kind of, so how it's like, okay, I need to build the hardware, let me learn hardware, then I can build the hardware. So,
I know.
yeah, share some of the experience
Sure.
with us, because I get told, go ahead and build the hardware, then you might be, what am I
Oh,
gonna
sure.
do?
Yeah, that's a very good, question. So I agree, I'm a software background, when I start working on RFID, so I know nothing about wireless communication. The good thing is I have a really awesome, lab mate with a EE background. He has a solid knowledge on EE. I always talk to him, asking some dumb questions and learn step by step, read books. It takes time, but as long as you believe this is a really important area you want to work on, you should spend time on that, right? Because for system work, for the system research, it usually takes a few years to build a whole system, right? So I think, calm down and, spend time to read papers, to read textbook. Textbook is really important. And also talk to people, learn from people. This is actually the key. I will not take it as a success, but the key to the, to working on some new area you are not familiar with. So I'm not familiar with the hardware. So after the PhD, we believe the hardware is very important. We want to build a new hardware because we notice there's problem with the conventional RFID system. We know this is the important area we want to focus. So we start finding a good partner to work together. For example, for our first RFID radio hardware platform. We work together with the EE guy. And after that, you know how it works, right? You can learn by yourself and you start like fabricating, start debugging, and step by step. This is how it works out. I mean, most of the time, I think people just don't want to waste the time to learn. I think this is a challenge or this is a problem. That's why you always want to leverage your domain expertise to solve problems, right? But research, always need you to keep learning, I would say.
That's a great point. Many times people just want to get my things done. I don't want to learn. But if you want to step a little outside your comfortable zone, then that's the payoff. I watch him starting from a software engineer, only know writing C++ code, I guess, at that time. And then now he can build all this kind of hardware stuff. So this is something I highly encourage you. UD in general engineering, I joked with him today when I met him. UD engineering is ranking higher than Pittsburgh, right? So that you have a lot of potential colleagues here talking to the students within the college. So you can if you want to build stuff, wires, mechanic, you have a lot of expertise sitting in this university. So encourage you hopefully. By the way, his big boss was his big boss, Dr. Victor Ball. Victor Ball is serving on our department advisory council. So he was here last year, earlier this year during the research day. Some of you probably get a chance to talk to him. So it's we actually have a pretty good, kind of connections with them. So because of time, so we will just stop here. So if you have any questions, particularly, I'm really interested in that the RF transformer. So if you are interested in maybe sending him an email, longfei@pitt.edu, right? Yeah, send him an email, getting a couple of this, maybe it could be very cool for your health, agriculture, this type of project.
Yeah, feel free to send me email. We'll definitely send you some hardware program. Yeah.
Okay, so we are so fascinated by his talk, we forgot to give him a applause. Let's